And when it comes to nomenclature, people are like, it's just an answer. It is this name. There is no work to show. Okay? To that end, I'm going to show some work. Okay? And we're going to push this all the way out to its absolute extreme as to all of the thought processes that need to be going on as you move through and solve these kind of things. And if you are not moving through and doing those things, you will likely make mistakes, which is why you should be showing the work. Okay? Our time is 30 seconds. This first one, metal, non-metal, ionic, non-covalent, carbon, so CO covalent, lead, PB acetate, I'll come back to that, but lead is a metal, which means ionic. The question mark probably means that this is ternary. So I could probably actually call this ternary ionic. So we go back up to the top. There were only two elements there, so I could call that binary ionic. Cr, because I've done a good job from Unit 1. I know that to be chromium. O, I know to be oxygen. Because it's in a compound, that gin needs to become ide, and it becomes, whoops. Let's cross out that Y, because oxyide, that just sounds stupid. So we'll make it oxide. The next one, I've got nitrogen. Oxygen again. Oh, but I just did that before. So we'll call that oxide because it's in a compound. This one, because it's covalent, I can use my Greek prefixes. So 2 in Greek happens to be dinitrogen. 5 in Greek happens to be penta. That sounds really weird. Hopefully it's multiple choice. It is. Tricarbon dioxide. I already started to specify some stuff. There's a C, there's an O. Tri was 3. Whoops. Di was 2. I meant to color code that differently. Oh well. Lead was PB. This 4 was the charge, and in particular the charge on lead. So that is actually PB plus 4. Acetate, okay, because I'm ridiculous and I happen to memorize all of my polyatomic ions already, I know that that is C2H3O2, and it has a -1 charge. When putting that together, I have to make sure that the charges sum total out to be 0. So I would need to know how many of each of those were in there, right? So I need to solve that expression for x and y. Not very good with the algebra, so because of that, I'm just going to guess. I'm going to guess that y equals 1. So x times 4 would just be 4x. Because I haven't solved for what x is yet. -1, because I said y was 1. So 1 times -1 gets me a -1 equals 0. So I would get x equals, sorry, I said I was going to show work, so let's actually do that. Add 1 to both sides. 4x equals 1. Divide both sides by 4. Hey, look at this. X equals 1/4. I can't have a fourth of an atom, so that guess was wrong. Okay, so I'm going to guess again. I'm going to guess this time that x equals 1. I mean, I did y equals 1. Let's try x equals 1. So 4 minus y equals 0. Add y to both sides. And I would get 4 equals y. Y was the number of these acetates I've got locked into that. That's a whole number. X is a whole number. Cool. So I'm going to drop those in there. I get x equals 1. Y equals 4. Certainly not 24. So I'm going to put parentheses in there to make sure it's clear in my approach for that formula. If we double back through that chromium, as I spit all over stuff. Oh, for the record, I'm over 4 minutes for the record. I needed to make sure the charge actually balanced out there. Charge on the chromium versus the oxide. Chromium's one I don't know the charge on, so I have to specify it. How do I specify it? Big old hint in the last one, I need to use Roman numerals. So what is the charge on that chromium? Well, the oxygen I know is a -2. I know there were 3 of them. The chromium I don't know, and I know there were 2 of them. I know if I added all that together, that would have to equal 0. 2x minus 6, everybody agree with that? Equals 0. 2x equals 6, we okay? X equals 6 over 2, which equals 3. I report it as a Roman numeral. 1, 2, 3. Whoa, man, that's what you get for showing work. Chromium 3 oxide, dinitrogen pentoxide, C3O2, Pb, parentheses C2H3O2, end parentheses 4, 6 minutes. Total, we started a half an hour in, so that was 5 minutes, 30 seconds for all of that work. Did anybody even come close? Okay. For the level of work that you should be putting in, when people are like, it's just a name, you just got to write it down, I call BS. Okay? There are so many layers of information that go into this, it isn't just a name. So when someone says it's just a name, what did they do? They internalized all of that. Okay? They've had enough practice at it that when they internalized it, they did it correctly. You haven't had that practice, which means when you internalize it, you do it wrong. How frequently do you do it wrong? Well, it's kind of up to you to decide and figure that out. But I would argue if you've done it wrong more than, 20% of the time, you should be showing your work. Okay? 80% correct is not good enough for me. Does that make sense? It can be good enough for you. That's your choice. Okay, but for me, that's not good enough for what I want you to do. I want you to do more. That went kind of fast, yeah? Yes. Did I show all the work, though? Can you show all the work? Yeah. That's what you should be doing. Not A. Okay? So there was a bunch up there. Do you want me to go over any one of those in particular? Like I can delete it all and then I can go back and specifically zero in on some if you would like. If you're just happy with it and you're just like, I just want to get done with it, then I'll move on. I'd be more than happy to move on because I don't like it.
So I noticed that with the ionics and the covalents that the ionics mostly have the charges and the covalents don't. Is it mostly the ionics that actually have to do the charges?
So observations. This is actually why on the very left I identified what type of bond was there. The rules change depending on the bond. This is why it's really important to know what kind of bond is there. This is why we looked at chapter 12 that referenced different bond types. We did that first, right? Chapter 12. And then we went to this chapter. What chapter is nomenclature? 6. When does the book think you should know what kind of bond type it is? Yeah, it's a little weird, right? So yes, the rules change for the different bond types. Why? The reactivity for those individual bond types is different. So if I name it differently, in the name, I've encoded some reactivity. That's cool, okay? And that's why the system is invented. Okay? It's useful. It doesn't mean I like it. Right? I don't have to like it. We just have to use it. There was another hand. Was you down?
Yeah. How do you know Roman numerals for the first one?
Roman numerals for the very first one. So when we go through to look at an ionic compound, going from formula to name, okay, there are certain elements that have different charges. Because they have different charges, you have to specify what charge it is in the compound. That information is embedded in the formula. Okay, so we have to be able to tease that out. Okay, so you'll look that I have a bunch of work there. Can I erase everything? Is that going to be okay? I mean, it's a lot, right? It kind of hurts. So So we go through and look at this. We had our chromium and we had our oxygen. Okay? What is the overall charge on this compound? How do you know that?
It has to be zero.
No,
It's not specified.
it's not specified. Okay? Because if I switch to the compound SO4 minus 2, what's the charge on that one? Minus 2. So it's specified to you. It's always given to you. In chapter 6, most of the compounds we're looking at naming happen to be always 0. That is not an absolute truth. Okay? And so that's why you got to be careful with it. Always look to that upper right-hand corner to see what the overall charge is. If there's nothing written there, then it is 0. So when I look at the charge contribution from the chromium and the charge contribution from the oxygen, they must cancel each other out to get an overall 0 charge. Okay, that has to be the truth. Okay, that's what that formula tells me. Okay, so how do I go through and figure that out? Okay, well, let's say I had a charge of +1. If there were 2 of me, what's the overall charge? +2. Each of me is a +1, right? Okay, so the amount is important when figuring out that overall charge. So what we can do is further divide this out into the numbers of chromium plus the charge on an individual chromium. Okay? Same thing's going to apply out for our oxygen. The number of oxygens times the charge on that oxygen. When I add that all up, that has to equal my overall charge. Okay? So if we looked back at the work that I had, that's effectively what I started out with. Okay? That information was embedded. I had that held, and I just started to do substitutions. How many chromiums are in my formula? There were 2 in the formula. That's what that subscript is referencing. Okay, so remember, we talked about atomic notation. We referenced charge and quantity off of the symbol. There's where it's coming in. Okay, what is the charge on the chromium? Well, I don't know yet. Okay, so that is a variable. In this case, I'll call it x. That can be any variable you want it to be. Plus the number of oxygens. How many oxygens are there? There are 3. Times the charge on the oxygen. Okay, that becomes a little bit more challenging on deciding what that charge is. Okay, for ionic compounds, we're responsible for knowing the charge. Did we talk about that? Yeah, actually we did. We talked about that last Tuesday on that slide that was isoelectronic, and we referenced the common ionic charges. The common ionic charge for oxygen was -2. When am I allowed to use that? It has to be an ionic compound. Okay, so it has to be a metal and a nonmetal. That's when I'm allowed to say it's -2. Okay, because I have a metal and a nonmetal, this is ionic. Cool, it is -2. What's the overall charge? This we specified above as 0. Now when we go through to solve, 2x minus 6 equals 0. Add 6 to both sides. 2x equals 6. Divide both sides by 2. And we get x equals 3. Okay. What did I say x was? Don't tell me 3. Was it the number of chromium? It was the charge on chromium. Okay? So the charge on chromium was a 3. Okay? And in this case, a +3. So that needs to get embedded back in my name. Okay? My name has to show me the charge on that chromium. Why does it have to show me the charge on the chromium? Because it's an ionic compound. And for ionic compounds, you have to specify the charge if it's not a standard charge. How do we know chromium's not a standard charge? Which is a really crappy question, and I fully admit that. How do we know chromium's not a standard charge? Starting to hear some knots. It's not group 1, because group 1 is +1. It's not group 2. It's not zinc. not cadmium, not silver, not aluminum. Because it's not those, I need to specify the charge. Okay? So if you don't know those charges that I told you to memorize, you can't solve the question. Okay? Or you can't solve it 100% correct, and we can look at that in a second. So we put it all together. We've got our name, chromium. There's our charge, Roman numerals was a 3, and then oxide. That's where the Roman numeral comes in. All of that glorious mess. Okay, do you have to do all of that? No. If you can internalize that and figure out how to do that in your head, that's fine. The one method that I will suggest you not use is exactly what the textbook shows you. They talk about this crossover method. It is the biggest load of horsepucky ever. It removes all of the understanding of what's happening, balancing out charges, in form of just swapping some numbers around. It has massive loopholes in it. Those massive loopholes will be exploited on exams. So if you want to use the crossover method, just be aware, I will find your weakness.
So for ionic bonds, it's cation, then anion, and then I gets put on the anion.
The order in which we name things, cation, anion, holds true for both the formula and for the name. Right? The anion part, the one that shows up second, the ending becomes "ide." We change it to an "ide" every time for an ionic compound. Is that good enough to delete? Any others? Nothing like getting an exam back and then going into a bunch of memorization rules. Make everybody feel like crap. You want help with the second one? Okay, so when we look, by second you mean this one, right?
Yeah.
Okay, so we identify the pieces. Okay, number one, is it ionic? Because we get different rules. For it to be ionic, it has to be metal and a nonmetal. Nitrogen and oxygen are both found to the right of the staircase, which means they are nonmetals, which means we're looking at a covalent bond. We don't have to worry about the charges or the ions. Okay, but that means we have to change the naming so that we don't get it confused. So in that change the naming, it becomes a little bit easier to do. We'll name these left to right, just as like we did before, kind of as cation, anion, but just follow the name or the formula. We'll tell you the order to write it. Nitrogen, and then the second one becomes oxide. You change that suffix. We need a different naming system here so that we can differentiate it from the ionic. The ionic used Roman numerals. In this case, we'll use Greek prefixes. How many nitrogens are in that formula? 2. So I use the prefix di. For oxygen, there's 5. So penta. This is where my weaknesses with nomenclature come in. Pentaoxide sounds kind of double vowel-y and sounds a little weird. So I would probably call it pentoxide, because that sounds cooler to me. Those people being, that's a stupid way to do it. That's how I do nomenclature. Back off. Okay? If it sounds cool, it was probably right. If it sounds stupid, it was probably wrong. Probably. Okay? And then there it is. That's it. So you name each of the pieces. The second one becomes an "ide" ending, and then you just specify how many of each of them there were at the beginning of the name. That's it. Way easy. The covalent ones, usually people get really quickly and easily because it's a lot more explicit. The ionic ones become more challenging because you have to deal with all that balancing of charges and stuff. Okay? We talked about how negative signs were a pain, and everybody laughed like, that's not a big deal. Who cares about a minus sign? That's why you're screwing up your charges. Because it's involving negatively charged things. Okay? The minus sign is why ionic compounds suck to name. Okay? With this, okay, really what this comes down to is practice. So yes, you want more, but I don't. So do it in lab. Okay? Lab number 6 is a nomenclature lab. Okay? You have 5 pages of just naming compounds. Okay? It is the lab that you do next week, I think. Yeah, it's going to suck. If you thought the Lewis structure was bad just sitting there and working on stuff, nomenclature is so much worse. Okay? And it's going to come down to, do you know the rule? If you don't know the rule, you're wrong. Period. Full stop. Might be handy to have a little sheet that tells you what the rules are, so they were easy to find. Instead of having to go through and watch an hour-long video to find all those rules, you could go to the tutoring center, where they have this handy-dandy sheet with a flow chart on it telling you how to go through and name. And it lists all the rules on the back side. Okay? Memorizing the rules is one thing. You have to be able to apply them. That's going to come with practice. Okay? I'm going to pause the video real quickly for this one. So, what do we got here? What we got right here is probably something a significant portion of you need, because you seem to be drifting off. It's caffeine. Right? Do you want to have to draw everything out like that? No, why not? It looks painful to draw that all out. Believe it or not, organic chemists go through and do draw things out like that. We also think it's a pain in the butt, and we make a lot of simplifications behind it so we don't have to see all that. Okay? For the sake of this class, we simplify it stupidly excessively. Okay, so what could we simplify that down to? I heard COHN. Good start. Don't worry for getting this part wrong, but officially oh crap, I'm going to get it wrong, I think. CHON. Okay? Why? The order in which you put them is supposed to be important. Not for this class. Don't stress. Okay, so there's just one carbon in that structure? No. So is that a good formula? No. So you've simplified it. I like that. You simplified it way, 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 way too much. So don't simplify it so much. What could you add?
Why do the oxygens not follow the octet rule?
The oxygens are following the octet rule. There are simplifications that we do in organic chemistry called not showing lone pair electrons. No one's actually called me out on that. Way to go. Show off. I think I covered them all. The other nitrogens. Thank you. You're a show off too. Okay. So yes, they do still follow the octet. C8. There's not one, there's 8. I'm trusting that you counted that right. Okay. So we would provide a formula to represent all of those pieces. The formula encodes some information. It also loses a lot of information. But that's what we're looking at when we look at nomenclature, is what is that formula for that compound, because it gets us some stuff that we can manipulate and use. For most of your fundamental class, in fact all of it, and for Gen Chem, we just use formulas. When you move up to organic chemistry, you realize that that formula could represent a whole bunch of different compounds. One of them could be caffeine that keeps me awake, and one of them could kill me. So it's really important to look at the structure. Okay? But structure is more difficult, so we have decided that you can't deal with it, and we simplify to formulas. Make sense? Should be mildly insulted. Okay? So we've got a bunch of formulas up here. What do all those formulas represent?
The different bonds.
Okay, we could start to think about different bonds, but that becomes difficult. When I look at H2O, is that HHO? For H2O? No, it was HOH. So your statement that there's different bonds. There are different bonds, but the formula doesn't show where those bonds are located, so I would say no, it doesn't tell you about the bonds necessarily. Say that again? You could look at it as the different ingredients that went into it. That works. Okay? Not only does it tell you the different ingredients, though, it also adds one more piece of information. What are the ingredients that go into H2O? Hydrogen and oxygen. That's it. So I could take 2 hydrogens and 2 oxygens and I would have water?
No, that's H2O.
No, that would be death. Okay? So it's not just different ingredients, it's how much. It's the number of those. That's telling me how much of those ingredients need to go in. So when I move to the next compound up here, how many oxygens? 6. How many hydrogens? 6. Cool. How about the next one? Let's erase all that because it's too many boxes. This guy. How many oxygens? 2. How many hydrogens? 3. Wrong. 4. Why is it 4? There's a 3 in there. Why did we split the hydrogen off? Okay. We're splitting it off because we're trying to show something about the reactivity of that compound. So we are changing the organization of our formula to give us a little bit more information. Okay. What is that more information? Well, we'd have to add just a hint more. That formula now gives me some information. What did that information just give me? It's an acid. I have a hydrogen in front and an aqueous in back. I now know it's an acid. That's information. If I had instead written C2H4O2, and I could even include the AQ, I don't know if that's an acid. It could be, it could not be. Okay? So we can change how our formulas are organized to reveal different bits of information. Okay? How else could we organize things? What does that mean to you in the orange box?
Why doesn't the H2O represent the 2 oxygens?
Okay, so we could look for discrepancies. On the left-hand side, we see O2. The right-hand side only says 1 O. Okay, that's fine. So the numbers don't match on there. But why would that matter?
Where did the other oxygen go?
Why do I care that there's another oxygen? You're assuming something is set up here, and you're right. What does this show? A reaction. We are starting with reactants. We're mixing those things, and they become H2O. So your assumption that that O has disappeared, okay, is only valid because you've implied that there's a reaction. The location of where we specify things around an arrow changes the meaning drastically. Okay? You will notice that, yes, the atoms don't tally up to be the same on both sides. That could be a problem that we will address in this unit, but not right this second. Okay? So we're trying to figure out how we encode that information and present that information when we're looking at a formula. Okay? That's the biggest deal to get out of this. Okay. How could we go through and measure these things? Okay, well, measurements. We've got distance, length, mass, volume, and time. Right? How would we measure those? We'd specify a number and a unit. Okay? That unit has 2 pieces, a measurement and a substance. Okay? I say 6 feet. What does that mean to you? It just means 6 feet. My son is 6 feet tall at 3.5 years old.
That's a problem.
Did that meaning change?
Yes.
Yes. Okay? A measurement, okay, a unit is what is the measurement that you took and the substance tied to it. Okay? When you write down a measurement, you'll have the number and then you'll have that measurement unit and the substance unit. Okay? The substance unit carries a lot of meaning. If you delete it whenever you write it out for your work, you're losing that information and it can result in drastic calculation errors. Okay? So when we're looking at our measurements, make sure all of those things are there. Okay? Our metric system, meters, grams, liters, seconds, right? All familiar? Right? Kind of hoping we kind of slide through some of this. Okay? Measurements with uncertainty, where's that error? Or where's that arrow? Tell me where the arrow is. Okay? So this would be 0.1, 0.2, 0.3, right? I'm trusting that someone got 0.8, 0.9. Hey, there we go. So we could say it's at 0.7. Is it at 0.7? 0.75. 0.758? Okay. I'm now starting to report more numbers than I'm capable of reporting. The device doesn't give me that information. So when we take measurements, we have to report out your absolutes, or what I call truths, and then you get one guess. What happens if you report another number? You're guessing on a guess, which is called BS. That's not science. That's biology. Boo. Okay? That information is what is implied, and this is where significant figures come into play. All right. So with that, we'll go ahead and stop. We'll pick up there on Thursday.